Okay. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as we can. So we'll generally be prioritizing questions asked in person over privately messaged questions. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they're speaking and also have their video on if you are willing and able. Lastly, for those of you who are joining us for the first time today, and if this talk is the first time you've received one of our emails, please sign up to our Chilloquium mailing list on the link I just posted in the chat. This is just to make sure we don't miss sending you the invitation in case you're not already in our mailing list, such as on the Harvard SPS list. And if you signed up last week or in a prior week, you don't have to sign up again. Otherwise, I'll have to take you off the list. It's another extra step. We send out one weekly Chilloquium email and a reminder on the day of the event. So if you want to stay up to date on what talks are coming up, fill out that quick 15-second form. All right. So with that, let's go ahead and get started. Professor Houck's research utilizes circuit quantum electrodynamics to explore both quantum computing and quantum simulation. One component of his research explores creating new superconducting qubits for use in a quantum computer rather than the implementation of small algorithms. Quantum simulation focuses on using superconducting resonators and qubits to simulate photonic lattices and explore condensed matter physics principles. The Houck group investigates new fronts in superconducting quantum computing and quantum simulation, tackling problems ranging from building a better qubit to understanding the many-body physics of a quantum impurity in a photonic crystal. Professor, thank you so much for joining us today. Looking very much excited for your talk.
Thanks for inviting me. I will happily talk. I think I'm hopefully following the instructions right, and I will talk sort of the first unknown percentage of the talk about my trajectory through physics and how I came to do the things I do. And then I'll give an abbreviated version of, a scientific colloquium where I'll talk about actually the work going on in our group. And yeah, please ask a lot of questions. I'm, happy to talk. So let me share my slides. Chilloquium. Can everybody see this? Yes, good. Okay, I'm gonna talk about sort of my work, superconducting circuits from materials to mathematics, and also how I got to where I am and random unsolicited advice, which is really exciting because that means I get to talk about myself and I get to give unsolicited advice, which are like two of my favorite things in the world. So, so I feel like this is going to be super fun. Okay, so. I've always liked math and science, so I knew I was going to be doing something mathy or sciencey. And when I got to college, I started as a physics major because it was super fun, and so that was great. But then after a while, I got to feeling like that wasn't that useful for the world, and it was very self-indulgent. I would study the mysteries of the universe, but that was more about me than anything else. So then I became an electrical engineer, and it was very practical, and I felt like I would do something useful and impact the world. But it also felt like the time horizon on which everybody talked was very short, and it just didn't have the same kind of fun. So I switched back to being a physics major and then back to being an electrical engineer. And I think I sort of switched back and forth quite a few times and really didn't know what I wanted to do when I heard a great talk about this new field that was arising called quantum computing, which was something fun and practical. It's a way to actually do something applied and study the mysteries of the universe all at once. So I didn't have to have this internal competition between the two parts of myself. And this was, I was class of 2000. So, this was a few years after Shor's algorithm in the Wild West days of quantum computing, when everybody was kind of proposing, this thing could be a quantum bit, and this thing could be a qubit, and this thing could be a qubit, but very little had actually been demonstrated. And so it felt like this really exciting time to jump in and figure out, can you actually make some physical system, preserve quantum information for some long amount of time, and really it was wide open, and there was there certainly was no industry, but there really weren't very many experimental demonstrations of anything like a qubit, or certainly there hadn't yet been a superconducting qubit that happened in 1999, the first superconducting qubit. So it was really at the start of all of this stuff, which was a fun thing to join in. So now I graduate from undergraduate, I go off to graduate school, and I decide, I'm going to do quantum computing. And I feel like my graduate school had this sort of like branching timeline trajectory where like I had this envisioned path through like what I was going to do in graduate school. And then I spent the entire time thinking about all these other things that I ought to be doing instead, because grad school for me was a really rough time. Like I started with one group. It did not go well. I worked, 100-hour weeks and still didn't satisfy my advisor, and I wasn't very happy. So I eventually left that group and had to find a new advisor. Experiments are hard. So at some point I thought I would quit grad school and go teach, and at some point I thought I would quit and do an industry. And it's like, and it's not just like idly thought about these things. Like I applied for all of these jobs that were. I really went through all the application process and got offers of teaching jobs or other jobs, because I really wasn't sure that I was either well suited or cut out for or enjoying graduate school. But every time I trimmed that branch of the timeline and was like, okay, I'm going to stick with this. And so in the end, I made it through graduate school. After my first unsuccessful attempt at finding an advisor somewhere in year 2, I switched to join electronics group at MIT. I was a Harvard student for grad school, but I worked at MIT. There's a joke I always use here, but it's insulting to Harvard students. I can't use it in this drive. So I went and worked with Ike. Ike was a new faculty member at the time. He had come from IBM's Almaden group and had been doing NMR quantum computing. He had literally written the book on quantum computing. And so, as a person who finally, found this thing that I wanted to do in life, I joined Ike's group so I could do quantum computing. And I think to this day, I am the only Ike student who didn't do quantum computing. So Ike had built his career on NMR quantum computing. But it was clear at that point that he had factored 15 and found it was 3 times 5 right before I joined his group. It was 70% of the time or something like that. It was 3 times 5. And so it was clear that NMR quantum computing wasn't going to be scalable. They'd done a proof of principle for all of the early algorithms. And so Ike decided to jump field into something new. And I think that's something I really admire about him and have tried to take away from him, which is to recognize when a field has run its course and when you can, do more by making a big, bold change. I think too often as a scientist, it's easy to stay doing what you're doing long after when the really interesting stuff has been done, because that's the field that you are the best at. That's the field you founded, and it's really hard to jump into a field where you don't really know what you're doing and you've never done anything and you might not be the best or even respectable. But that's something that he did. And I was sort of the student that was in the wandering through the desert, doesn't know what he quite wants to do phase, right? So I became an ion trap professor a little bit after me, and he was an NMR quantum computing person before me, and I was the sort of wandering in the wilderness students exploring different things that might be fun. And so, the 2 projects I did with him, I made negative index refraction materials. We made one of the first materials in the microwave regime that had a negative index refraction, and we did Snell's law experiments, and that was fun. And then we did some single molecule transport by building these electromigrated break junctions, and you take these tiny little bow tie wires and you flow current with them until they break and they leave a nanometer gap, and you can put stuff in the gap and do quantum dot type transport experiments there. And I would say, both of these things were totally fine, solid work. People read the papers, people liked it, but I didn't feel particularly that accomplished. So I wasn't sure I wanted to go on to be a faculty member or even do a postdoc. So I thought about, what random other jobs I could get. When this guy, Rob Shulgoff, came and gave a talk about circuit QED, which he had just sort of published the first circuit QED paper. And then it sounded super exciting. So I figured, okay, I might not be cut out to become a faculty member, but I'll go try this postdoc for a couple of years. And if it seems fun, maybe I'll keep going. And if not, maybe I'll do something else. And so I jumped to Rob's group. And then like the very first thing we did was try and come up with a new qubit, which we eventually named the Transmon Qubit, which is this sort of thing you see in this picture. It's now the superconducting qubit that's used in basically every industrial quantum computer, every superconducting industrial quantum computer. So this is something that IBM uses and Google uses, and and the vast majority of groups still do most of their research with Transmon Qubits. And because it's this sort of simple, kind of easy to use, kind of hard to screw up qubit. And so that was great. So I had this qubit that everybody liked. So I wrote that to, I guess, to a faculty job, and basically I would just ride that for the rest of my career. Like everything is sort of a trickle down from happening upon that just at the right time at the start of a postdoc. And so so I think what I think is interesting about this is I didn't suddenly become a better scientist. Like nothing I did. I think it's all good work. And I'm proud of it. But I don't feel like I suddenly became a better scientist when I started in Rob's group than I was in Ike's group or in the group before that or at any point in my career. Whether something really takes off and has impact or not, I think is less a testament to how good of a scientist you are and more like, a whole bunch of things that are also outside of your control. Like, does this did this thing happen to work really well and take off, or did it happen to work fine and be interesting, and then people move on and look at the next thing? Right. I think you do solid work and hope eventually something pans out. That's what I learned from this. So then I went off and became a faculty member. I got a job at Princeton in electrical engineering. So not all cool physics happens in physics departments. I'm actually in the electrical engineering department at Princeton, which is where I think a really large fraction of the quantum kind of work is. And I had to think about what projects I wanted to do as a faculty member. And I always think of this like how to choose new project. It's the Venn diagram of doom. Because you definitely want something that you know how to do, right? Like if you don't know how to do it, you're not going to make much progress. It's best to have a project that like no one else is working on. If everyone else is working on it, then even if you happen to be the first one to get it done, you're not impacting science that much, right? Like if I can do something like 2 weeks faster than someone else, and so I get my name on a paper and get a big, like hurrah. Like that's not that exciting to me because someone else would have done that anyway. So I'm boosting my own personal stature. Like I'm not changing the field of science or human knowledge or anything like that, right? I'm basically just like racing people to take credit for something that's clearly going to be done. And of course you want something to be interesting, right? And interesting means not just interesting to you, but like the world considers interesting, right? And it's often it's pretty easy to find something that satisfies two of these things, and it's really, really, really hard to satisfy something that describes that has all three of these. And if you can find anything in that middle, then I think you have a great project, and you're going to find something new and exciting and wonderful. I think very often the world feels a little bit more like this, where there's really just no middle. And so there's these intersections, and so like those can be fun, right? Like you don't want to ever do nothing. So sometimes I feel like I'm out of great ideas that really are at the middle, and so then you have to decide what to do. And so you can pick, right? So which of these three like overlaps do you want to work? And this top one is science fiction, right? If you don't have any idea how to do it, but it's interesting and no one is working on it, that's like science fiction. Like time travel would be super interesting. I don't know anybody working on it, but I don't know how to do it, right? So not so good. Like that's a part of the Venn diagram that you can write about and you can dream about, but it's I wouldn't work there. I'd say if you work at this sort of intersection between interesting and how to do it, that's where you get your nature papers. That's like the nature and science glossy papers that like people care about a lot. I think in if you can't get them from the middle, you're most likely to get them here, because if you know how to do it and people think it's interesting and you happen to be the first one there, you're going to get a fancy paper. But again, I don't like working there because I feel like I'll get a paper, but it's about my own like personal glory rather than really changing science. So if I can't come up with anything in the middle, I like to work here, which is picking ideas that no one is working on, and that I know how to do. And, at least I have to find them a little bit interesting, but maybe, they might not seem like the most important thing yet in the world, but like there's a potential there. And, if you work there, you're looking in new corners, and sometimes that means you're going to be doing something that like relegates you to obscurity. But there's really a potential for surprise, and physics in the world is much more surprising than we give it credit for. And if you look in places that maybe aren't interesting yet, but you have a hunch might become interesting, then if you know how to do it and no one else is working on it, there I feel like is like my personal like go-to place. Maybe it's not this far over, maybe it's like a little bit closer to the middle, but if I can't find anything at the full intersection of the Venn diagram of doom, then I roll the dice and go for like obscurity with the potential for surprise, then trying to get the race to the Nature paper, but maybe just racing other groups by a little bit. But this is sort of how I view like science and my personal biases in terms of where I like to work and how I like to think about projects. Okay, so that's how you choose a project. And then it's about doing physics, right? And I think we often equate doing physics with just research, but especially as a faculty member, like doing physics is not just doing like physics research. There's many aspects to this job, and all of them result in sort of an increase in our knowledge and understanding of physics, and they all act in different ways. And what I find fun about this job is that you don't have only one thing that you're doing all the time, right? So I love research; it's great. I also love teaching. And teaching, there are many opportunities here for you to spend your time. So teaching can be just like, I'm going to take the courses I'm supposed to teach, and I'm going to teach them to the best of my ability. And that's great. You can also apply your, scientific thinking to, teaching problems and think about it like a scientist in a research way. So something that we noticed at Princeton is that we had a relatively large degree of attrition during our first year curriculum from our engineering program, which was math and physics courses. And if we dug into the data and looked at demographics, like it was attrition that was substantially worse among groups that were sort of trying to retain to promote diversity within our departments. The attrition rate among women was much higher than among men. The attrition rate among Black students was much harder among white students, and this is a real problem. And so we did a 5-year curriculum redesign to address attrition in the first year, and to address especially the systemic bias in the first year attrition. And it's been remarkably successful. So our overall average attrition went down from 20% to about 8%. And that happened while alleviating all of the different kinds of achievement gaps I've been talking about. And so that was like a significant investment in time, but something that I think has really impacted the state of science at Princeton, even if it's not pure research. There's building, right? So at first you sort of build your research group, but now I look at the sort of scientific ecosystem. There are often these big centers you can build. There's one at Harvard, that's sort of university wide, and there's one at Princeton that's university wide, right? So at Princeton, we have folks who are in the physics department, who are in electrical engineering, who are in computer science, who are in chemistry. We're scattered amongst different departments. We have different disciplinary trainings, but we're all interested in the same kind of problem. So how do you build a structure that can bring people together across those disciplinary boundaries? You can do that on a national scale as well. So the Department of Energy and the US and the National Quantum Initiative Act has funded these big quantum centers that are, these many institution things. I'm about to start as the director of the Co-Design Center for Quantum Advantage, which is run out of Brookhaven National Lab, but it's a 24 institution, 88 PI, like mega quantum center, which is trying to bring together people who think like material scientists, and think like chemists, and think like physicists, and think like device physicists, and computer scientists and computer architectures, all in like one umbrella, and try and get them speaking the same language and scientifically thinking about these kinds of things, like thinking about the same kinds of problems. And then there's advocacy, right? So this can take many forms. It can be about trying to sort of look at issues in the culture of science and address them directly. Sometimes this can make you some some not friends, but I think as a professor, you have like a job and tenure, and so you have like, you know, in some sense, the ultimate in privilege, in that, you know, you can speak your mind and not get fired. And I think, you know, finding ways to use this this sort of platform to advocate for sort of improving the overall culture and climate of the scientific community is super important. It's something that I take seriously. And so I really sort of view doing physics not just as the pure physics research, though that's super fun, and I'm going to talk about my research eventually, don't worry. But it's sort of all of these things. That's like doing physics, and then of course there's something that's a little bit different from doing physics, which is being a physicist, which adds one more block to the like divide of your time, which is like life, right? It's like, you know, family, and for me, I have 3 kids, and spending time with my kids and trying to like be respectable, maybe slightly above average parents, or something like that, and at least not have them like crying all the time. Right. So there's all of these things that are about being a physicist, right? Because being a physicist is now sort of balancing all of these, you know, finding a way that you can take whatever you want out of life, whether it's, you know, a family or traveling or professional success, or, you know, working, like whatever, however it is you define your life, like you have these 5 things to balance, and I really sort of view being a physicist as like trying to embody all of these in different ways. And I think this kind of thing like really feeds into my imposter syndrome in funny ways. And so I'm trying to think about how to, in giving this talk, I wanted to think about like how I should talk about this. And I think in my mind, I'm like always like evaluating myself, and I'm like, how am I doing on these 5 topics, right? Like, you know, if I were like assessing myself right now, like my research is like pretty good. Like I'm relatively happy. You know, I'm clearly not like the best in my field, but I'm pretty good. You know, life is all right. Like I'm, you know, I think I'm doing a great job on teaching, and, you know, I'm a director of a big center, so I'm not doing so bad on building. But I like, you know, but I have these like 5 things that are really important to me as a physicist, and I try and build them all. And I think what happens in my brain is when I try and like feel like how am I doing as a scientist, I like think about one aspect of this, and I compare it not to like, sometimes I'll compare it to my peers, but often I'll even just be like, how am I doing compared to like, how could I be doing if this is all I care about? And I always feel like I'm falling short, because if the only thing I cared about in life was like research, then I could do much better at research, I think. You know, certainly if I like stayed at work till midnight and blew off my kids, I'd you know, make it a lot further. You know, but you have this balance, and you know, and so it's very easy to like look at one aspect of my career, whether it's research or teaching, and think like, you know, man, I could have, you know, I could have been so much better if I just really focused on this one thing. Or, you know, I'll feel like I'm not good enough. But if I sort of zoom out, what I see is like, this is really what, you know, what things would look like if I really cared about one thing above all others. I would like fail at life, and I'd be a pretty bad teacher. And, you know, maybe there's some things that don't take that much time, and they just take like, you know, being brave and willing to like annoy people and make people mad, that I'd be okay at. But like, you know, I would have this sort of very different overall set of outcomes, and I wouldn't really be happy about this. Like, all of these things are important to me, and if I looked at my life this way, then I'd be like, oh man, I'm such a failure at all of these other things. And so I think when I feel really, you know, it's easy in doing a job like this, right? Physics is a weird thing, because it's a super fun job, and you get to like discover all these things about the world, and you just like do crazy stuff. But it's also a field where, like, I don't know, if you're not making the very best discoveries, you can often feel inadequate. And I feel like trying to keep this perspective of like, you know, here's everything I care about, and I'm like really trying to like live this balanced life, and all of these things are important, and not be so hard on myself on any one aspect. Like if I start thinking like this, then that's super bad news. And so, you know, I feel like now that I'm a established and tenured faculty member, my daily struggle is not so much about how well I do at any one of these things, but it's about keeping the balance of all of these things, and not judging myself too harshly for like any one area where I could have done better if I blew everything else off. And so that's, I think, like life as a physicist. Yeah, anyway, yeah. What's up?
I have a quick question if I may interrupt. So
Please.
I'm interested, You mentioned your involvement in advocacy and cultural issues within science and STEM. I was wondering if you could elaborate a little bit on what you see as the more pressing issues within the culture of STEM and science, and maybe physics in particular, or physics and electrical engineering in particular,
Yeah.
and also the kind of consequences of not addressing these.
Yeah, I mean, I would say, clearly, I'd say the biggest challenge is the massive lack of diversity in STEM fields and in physics in particular, and more microscopically in quantum physics, and even more pressingly, I'd say in superconducting quantum physics, right? Like I'd say, the gender balance is entirely off. There's, maybe, 3 professors in superconducting qubit hardware who are female right now, and I think that's a huge problem, and it comes from a very large number of things, right? I would say, there's also similar problems along racial lines, and I would say it comes from a blend of people not doing enough when they see sort of clear leaks in the leaky pipeline to addressing them. They come from people not speaking out on sexual harassment issues, which we had a problem with in our department, and that led to a big fight. It comes from generally not supporting people and finding out from students like what they're struggling with, right? It comes from not being aware of mental health issues also, right? I think there's it's a tough time in graduate. I had a tough time in graduate school, and I think trying to understand where people are and just being able to support your students, that matters. I think there's also national advocacy. As a faculty member at a top university, I have a national platform, so I can take leadership roles and things, right? So I was the chair of the Division of Quantum Information in APS, and so I could speak to some of these issues sort of in professional societies. There's also ways you can advocate for other things, right? So there's ways you can sort of consult with the government on issues related to science and technology, whether it's national security issues related to science and technology, or how policy interplays with science and technology, things about immigration status, and there are ways that as a faculty member you can be a very valuable consultant to the government, and so there's sort of issues of culture locally at your university. There's sort of culture and issues in societies. There's sort of broader issues of like national policy, which is a little bit of a different thing, but you have an ability to speak, and especially to listen to people who don't have as loud and powerful of a voice, and to just amplify their voices. And I think trying to let students and people know that you're willing to do that, and I think is an important part of this job.
So I'm going to interject here really quickly and say that I was the other co-host, but I was abducted by pirates, and so I was absurdly late. But maybe this wasn't said earlier, but this is supposed to be somewhat conversational, so if everyone else could have their videos, or if you're able to have your videos on, that'd be really lovely. Professor Houck, I think, or sorry again if I'm mispronouncing, but yeah, I think it's super important that you're talking about these advocacy things, because I mean, even in Chilloquium, where there's a sort of natural platform for this, it's not super common, for faculty to speak on this. And it's really great that you are. There's kind of 2 questions I have about this. One is that you talked about at some point the privilege of having tenure and being, like well established in your field. And that kind of gives you not only a platform, but a sense of security to be able to speak on issues that you feel are important within your advocacy. But for students or postdocs, undergraduate, or et cetera, how do you see this sort of the interplay of like the risk of kind of excommunicating yourself versus like speaking out on issues that are clearly very important? Like, how do you see like balance? I don't know. This is not a formulated question, but poorly.
No, it's a really good question, and I would say in some sense it's nice that I have tenure and I'm in a privileged situation right now, because that makes it safer. I've always been outspoken and lacked like I've spoken my mind, but a lot of that comes from the fact that, you know, as a cis white male in physics, like, you know, I have some other forms of privilege that allow me to always speak out. I would say, you know, there are many ways that you can get involved. I think really being aware of what's happening, listening to people is super important. You know, even you know, if you aren't going to speak publicly, you know, trying to speak to people privately can be very helpful. I think in the end, you know, I think a lot of people are, you know, are hesitant to speak out, and so I think that's something, you know, it preserves the status quo if everybody is nervous to speak out, and I haven't I haven't noticed too much blowback, except there was one sort of rocky patch where I was speaking out on our sexual harassment issues, which I think, you know, I nothing explicitly bad happened, but I felt like nervous and out on a limb, and I felt like that's something I might not have done if I hadn't felt very secure in my position. But you know, but I think it's important to recognize, like, if you are in a privileged position, then like it's important to really, you know, use that privilege to amplify voices for people who are nervous and don't have that.
Mm-hmm. And on a separate note, maybe kind of along similar lines, but you're kind of like I think you said like applied engineering, or I've heard it's described as like some sort of like more applied focused courses that you've kind of introduced within the curriculum, and like for retention and other just purposes seem to have been very successful at Princeton. How well do you think these translate to other schools, and what, like, kind of under what conditions do you think similar implementations would like succeed at?
Yeah, it's a really good question. So we've measured, you know, that they are super effective, and we've been trying to figure out what it is about them that makes them effective, right? So I think one thing is we have very dedicated teachers who really bought into the idea of teaching this course, and that matters. We create a cohort, I think, in that process. You know, we advertise these courses as courses that sort of focus on more applied problems, especially, and we choose our applications around societally relevant grand challenges. And so a lot of research says that a lot of people who are underrepresented in STEM are attracted to STEM because of the ability to enact some kind of societal change. And we thought that would be a good vehicle to build the courses around. And that's really all we do to attract different students. But even in the first year, right? So we advertise these courses as, you know, you can learn the math and physics that you learn in your first year in courses that are more applied, and the applications are chosen from things like, you know, energy and environment and health and things that are really societal challenges. And just by advertising courses that way, we attracted a group of students that was you know, 2/3 women, and you know, the racial demographics were, you know, an incredibly different from what we see in STEM overall, and actually more reflective of the full campus body. And so it was a really very refreshing thing that in our pilot year we saw and attracted a much more diverse class. And the retention was highly successful. So I think some of that is like, we can attract a cohort around, you know, again, not saying like, oh, we're going to take, you know, whatever groups of people. We just build a cohort around people who are attracted by the same things. So I don't know necessarily that the applications are that important. I think it's that the people who bought in chose to be there for a reason that centered around some way of learning that they were excited about. And I think that really mattered. I think some of it is that the people who really bought into this just really believed in students. You know, we said, like, you know, that we are going to teach these courses and we are going to spend the time it takes to get people to really understand this content, because we believe every student who enrolls in these courses can be successful, right? You know, and I think this sort of core underlying belief that every student can be successful, right? I think matters, and that's sort of less about the particular content. But yeah, I mean, I think they can translate, right? So I've given talks about the sequence of courses at a handful of other universities, and I think, you know, I know a number of places are trying different things in order to see what works for them. Education is never a one-size-fits-all thing, right? there's things that we did that worked and things that maybe didn't work. Certainly the first year we taught it, one of our courses was a total disaster, and students hated it, and yet didn't drop out. The course ratings were like really, really bad because it was way too hard. But I think students felt well supported from their other classes and didn't drop out. So it's interesting to think about what matters in these things. But they've been, I think what I would say is the takeaway is not that, we magically figured something out, because even in the first year that we taught these courses, like one of them didn't work that well. But even though one of the courses kind of failed, the overall program was a huge success based on our metrics of attrition and differential rates of attrition. And so I think that means that, we just need to try things, right? And it's a sort of a proof of principle that, if you believe, if you don't just accept that, these kinds of rates of attrition are just par for the course and what you're going to get, and you fight to say that we believe in our students and that's not acceptable, then as you try new things, you can be successful and in whatever your local climate is.
And I see a hand in the audience from Yuting. You can go ahead and unmute and ask your question.
Yeah, thank you. My name is Yuting. I'm actually a Harvard student working at MIT. So I'm actually interested in the joke you didn't tell us. But anyways, thanks for telling us a lot about your values. And I think this is really, really important. And I think the previous two questions is already about this, how you apply it to a university or departmental level. And what I'm interested is, like, say, among your core values, and how do you apply it to running your own group? And that's my question.
Yeah, I mean, so I when you run a research group, all your advisors have different styles, right? So when you all go to graduate school, you want to find, an advisor who has a style that matches your own. And so I try and think that what I liked as a student and what I didn't like. So, for instance, I really hated being micromanaged. And so I try not to micromanage my people. I really hated, when I couldn't find my advisor for weeks on end. So I try and be like present. And so there's like a balance, in style that I try and do, which is like between, being present, but not too hands-on. But that might not be a good fit for everybody, right? So there's those kinds of questions. I think in terms of other issues, I try and be open about what I'm thinking. I sort of like I'm talking to you about here's my thought processes and my values, and I try and impart that as a thing that's important to my students. And I try and show that you can be reasonably successful and have what I think are hopefully good values, right? Because I'm an existence proof that you can I think often it feels like maybe you have to be cutthroat or something to be successful, or you have to work all the time and all of that. And I feel like I've been able to be moderately successful without doing that. I think I let my students, obviously there's some level of work people have to do because, I am stewarding money that's like the government's money, which is everyone's money. And I can't let people just not do work. But I also try and listen to my students and trust them about, when they work and how hard they work. And, sometimes I'll give them a push if they need it. But it's really trying to be aware of where every student is at and their, mental health and their success, and try and help them achieve what they want to achieve. I try and talk to my people a lot and find out what they want to do with their lives, right? Because not everybody has the same sets of priorities and the same vision. And I really want to try and help people realize whatever it is that they want to do. And so I think there's a lot of different advising styles and different goals change depending on really where people want to go and what they want to do. And so I think there's a lot of that goes into advising that's important. And I think I just talk about what I'm thinking about to my group, and that's I think that's gotten to a point where my people trust me. And then they'll bring hard issues to my attention, whether I'm screwing up or if there's just something that's going on that needs addressing, and I will like listen and really try and follow through on what they need, you know, and trust and action build more trust and action. And so I think it's sort of built a positive culture in the group. I got to say, when I you know, there's always a tendency, especially in terms of how hard people work, but in the way you work, to say, you know, I am going to work like crazy to get this job, and then when I get to a certain point, then I'm going to like live out my values. But if you have to like live in a way that is like opposed to your values in order to get the job, then that means you're probably going to have to live in that way once you get the job. And so I think because I was never so absolutely wedded to being a professor, like it wasn't something that I would have like died if I couldn't do, then it sort of made it easier for me to like live life with the right balance, that, or you know, the right balance for me, right? So make choices that I thought were right for me. And if I couldn't get a faculty job based on that, or if I couldn't get tenure living that way, then that meant it just wasn't the job for me, and I would go do something else. So I think by like trusting that, you know, by basically saying like I want this job, but I only want this job on my terms, then, you know, then I think I've been able to sort of not fret too much about how everything is going to turn out, and just trying to sort of impart that to my people by being an example or talking it through with them. So I don't know.
Thanks. Yeah, it sounds like you're very confident, like just like you're fine.
I mean, you know, like I'm a like I went to, you know, I was a great undergrad Princeton EE student, and I got a PhD from Harvard in physics. Like if I don't become a professor, like I'm gonna get a good job doing something and it'll be fine. And you know, if I don't get tenure, I'll like go teach somewhere else, or I'll go, you know, like you all are Harvard physics students. You're going to be fine in life, and you know, and so trying to sort of accept that you're going to be fine, and therefore can like live in a certain way and get the kinds of jobs on your terms or not, and still be fine and get a different job on your terms, right? Like I think, you know, so much of stress comes from like trying to preordain what your trajectory is going to be, and then being stressed that you're going to have to deviate from that trajectory and be surprised by some other amazing life that you're going to get, but maybe not the one you picked out in advance, right? Like, you know, life is going to be amazing for you all. Just like let it happen, and try and, you know, trust that it will be fine is sort of the philosophy.
And I think I see another hand in the audience, Keshav. You can go ahead and ask your question.
Hi. So I wanted to ask you something, because you mentioned something that's kind of close to my heart, which is the interplay of physics and engineering, because I bounced around a fair bit between electrical and physics. And I was kind of curious what your perspective is on this, because in a core level, quantum information, especially the theory side, comes from a very fundamental part of physics, even though right now it's kind of the most mainstream. And I was wondering if you essentially ever conduct things of a more fundamental kind in terms of experiments in your lab, because I was reading some of what you've written on your microwave cavities and nonlinear quantum optics. And I was thinking that there are probably at least a few places in fundamental physics where such setups can be quite beneficial. So I was wondering if you've ever played on mixing around with the two of them in your lab.
Yeah, I definitely do, and I'll like, you know, if I have time to do any of the research part of my talk, I'll talk about sort of the breadth of things that we do. But we do some like very dirty materials work where we can try to improve pieces. We come up with some new fundamental devices, which is like real pure physics Hamiltonian engineering for quantum information purposes. We do some many body experiment where we just build lattices of cavities and try and look at new emergent phenomena and understand, you know, especially nonlinear or non-equilibrium quantum many-body physics. We are now sort of doing a bunch of work, which is like looking at the relation between graph theory and mathematics in our lattices. And so, you know, I wrote my first like applied math paper in the past year. And so it's so somehow this one platform has sort of taken me like in the last year from like all the way to like very like dirty pure material science all the way up to like writing an applied math paper, and so I feel like what's fun about the research area is it's just like the sheer breadth of things I get to do with this platform. You know, I know people are using circuit QED systems, so I'm not doing this to do like axion detectors and things like that. And so there's all kinds of things you can do with these systems that are not applied. And so when I said like I found quantum computing is this interface, it really is. You know, I have this platform that lets me do some stuff on the science side and some stuff on the engineering side, and sometimes things on the science side give us new insight onto engineering, and sometimes vice versa. And so it's really it is a mix of both passions. It's not a compromise of both passions.
Okay, thanks. So I'm sorry. I know it sounds a bit less emotional than a lot of the other questions discussed, but I think I'm the first in my family to ever go into engineering, STEM, anything of the sort. So when I get to hear it discussed, it's kind of very enriching.
Thanks everybody for your questions, and they were all really great, despite being of different flavors. Go ahead, Professor. It
all
should
right.
be nice if we could talk about your research. Sorry for the.
We finally no, I'm glad for all the questions. It's great. At 5:19, 49 minutes into the Chilloquium, I can start the 45 minutes of research technical content I had prepared. Okay, I'm going to go a little fast through all of this and talk about the breadth of research in our group, but feel free to interrupt with questions, but I will give a slightly abbreviated version. And really, we're doing superconducting circuits, I say for quantum computing, but it's really all the way from materials to mathematics, so trying to span the full spectrum of the types of things you can do. So at our core, we have the most basic building block, an LC resonator. If you're an electrical engineer, you're like, aha, an LC circuit. It has a known frequency, 1/root LC, and your life is good. If you're a physicist, you look at this and you say, well, it's an oscillator. It can have photons, and we can write a Hamiltonian, which is like an omega A dagger A. So it's also a harmonic oscillator. If you want to build a qubit, though, if you want to use this as a qubit, it's not so good because you can sort of add 0 or 1 photon, but as you try and add 1 photon, you might add 2 photons by mistake, because this is a very linear system. All these energy spacings are the same, and that's not so good. But fortunately, in superconductors, we have this thing that is in X. It's called a Josephson junction. It is a superconducting, insulating, superconducting sandwich, and to a first approximation, the way to think about it is a nonlinear inductor. So rather than having a perfectly harmonic well, we have something that softens as you go up, and the energy levels get a little bit closer together. And if you think about that, what that means is that you can address the 0, 1 sort of photon spots without going up to 2 photons, because you don't have the right energy to go up to 2 photons. It's actually a little bit, the 1-2 transition is a little bit lower in energy than the 0-1 transition. And we call this nonlinear LC oscillator the Transmon Qubit. So this is the thing that we discovered when I was in Rob Schokoff's group. And this is the workhorse qubit for everybody's quantum computer. And if you sort of look at like the development of quantum computing over the years, in the early days, 1999 was the first superconducting qubit called the Cooper box. Information lasted about a nanosecond. Over the years, people have built, better and better qubits, and things have gotten up to the point, though in most of these sort of transmon style qubits, they petered out in the development around 100 microseconds, now almost a decade ago. But even though these transmons sort of petered out in coherence, people are building bigger and bigger systems. So Google famously announced that it could do something on a quantum computer that was hard to simulate on a classical computer, a result they called quantum supremacy. IBM has taken their systems and made them look like sleek and shiny and pretty. And they also have, 50 qubits of sort of quantum information with really good coherence times and all of this. And so people have built these into actual computers. You can go and you can do stuff on them online. And so sort of what is the role of an academic group in a field where, big companies are spending tons of money building large systems? Well, I feel like it's really to try and think about what's missing at the component level and how to protect qubits. And really, I would say it's thinking about sort of ways to make the individual pieces of a quantum computer better. And so if you have qubits living in a noisy world, you need to preserve these quantum superpositions despite, charges and magnetic fields and photons and dielectrics and surfaces and cosmic rays and all these kinds of things can all come along and kill your quantum information. And if you want to go and actually protect your quantum information, you really have three choices that you can do. And we like to think of these as the turn the volume down, you put in the earplugs, or you use the noise canceling headphones, right? So if you have noise, one thing you do is you can just turn down the volume. You could reduce the noise. You could use material science and engineering to improve fabrication and materials in order to improve coherence by getting rid of whatever's causing the problem. You could do an intrinsic noise protection. This is the earplugs approach. You could just build devices, new qubit designs that are passively insensitive to noise, or you could do active error correction, the noise canceling headphones, where you monitor for errors and you apply some corrective steps in a feedback loop. And you basically take these ideas and you can apply them to qubits. So if you think about reducing noise, so if you think about how long qubits should live, this is our LC oscillator. So this thing in the middle is the Josephson junction. That's the nonlinear inductor. And these blue paddles are pieces of metal. Those are the two sides of a capacitor. Here we do this on sapphire substrate and with superconducting metal, which is essentially lossless. And so you could say, how long should qubits live? Well, if you look at the research in the 80s that shows, what quality factors of resonators you can make out of sapphire, the coherence times should go up to, even with the worst sapphire, something like 30 milliseconds, and with the best sapphire, something like a second. But our qubits are limited to like 100 microseconds. So why is that? As Wolfgang Pauli said, God made the bulk, but the surface was invented by the devil. So the bulk sapphire quality is actually quite good, but surfaces can be super noisy. And if you measure the coherence time of a qubit based on how closely you put these capacitor pads together, you basically are measuring how bad the surface is. Because when these capacitor pads are closer together, then most of your electric field is confined near the surface, and you're more sensitive to loss near the surface. And the closer these capacitor pads get together, the lower the overall coherence is, in a way that sort of systematically makes sense if you go through the details. And this really tells you that the bulk sapphire is fine, but these different surfaces and interfaces are the problem. And so we, have one thrust of research, which is really looking at the material science and says, like, what's happening at the surfaces and interfaces. So if you look at the surface of niobium with X-ray photon electron spectroscopy, you can actually see just like a depth profile of what the oxide looks like. And you can see it actually has a pretty thick layer of oxide, and oxides can be pretty lossy. And not only does it have a thick layer of this stoichiometric oxide, which is the light blue, but it has like this really sort of pretty thick layer of this NBOX, which is this like non-stoichiometric gunky oxide, which tend to be super lossy. And if you look at the atoms at the interface between the niobium and the sapphire, the sapphire is beautiful and in a nice crystal like you expect. The niobium is somewhat ordered up high, but right in this like 5 nanometer layer near the surface, it's like super heavily disordered. And that disorder looks like it could cause a lot of loss. So we switched from niobium to tantalum, which took some time to learn to grow, but you can see that you can move from a thick oxide with a lot of suboxide to a thin oxide with a little bit of suboxide, and you can go from this messy metal substrate interface to incredibly well-ordered tantalum on top of well-ordered sapphire. And when you do this, the coherence goes up to over 300 microseconds, which is sort of a threefold increase over the state of the art. And that's really by doing a bunch of real material science where you measure properties of the system and then you correlate sort of standard surface spectroscopy techniques with qubit measurements of coherence. And this is sort of ongoing work to push this even higher. You could also build sort of intrinsic noise protection devices. And I'm going to just give the flavor of all of this stuff because, again, we have like very little time. But if you want to build intrinsic noise protection devices, the idea here is that you build a device that is insensitive to noise. And so this qubit that that everybody uses now is called the Transmon Qubit. and it has two parameters. It has a Josephson energy and a charging energy. This is like basically the size of the inductor and the size of the capacitor. And on the left here, you see sort of the energy spectrum from a device where the EJ over ECA ratio is small. That is, the capacitance is relatively small. This device is the spectrum of what's called the Cooper pair box. And as you increase the EJ to EC ratio, you see all of these bands get flatter and flatter and flatter. Okay. Now, what this means is that if you have a superposition of the 0 state and the 1 state, then the energy difference is incredibly well defined if you don't control this this applied voltage or this gate charge. Basically, if there's charges moving around. Whereas here, if NG moves, the energy difference between the 0 and 1 frequency is changing by quite a lot. And so by changing the EJ to EC ratio, you can change how sensitive you are to gate charges. And if the primary source of noise is like fluctuating charges, then you become sort of exponentially insensitive to gate charge. But it's still basically a harmonic oscillator, which means you can easily lose energy, right? There's a matrix element between the 0 state and the 1 state, which according to Fermi's golden rule says that you're going to relax. So the Transmon is a device where we've sort of designed the thing to be insensitive to charge noise, but it's very sensitive to energy decay because these wave functions overlap. If you build a double well potential, then there's no overlap between the wave functions of your 0 and 1 state, and so it's the matrix elements are 0, and so it's very hard to get energy to relax in the system. But any slight change in like the applied flux or the applied gate or the sort of environmental noise results in a change in the energy between the 0 and 1 state, and this leads to basically dephasing or T2 errors. And so if you have an ideal qubit, what you want is something where your 0 and 1 states live in different wells, and that makes it hard for energy to relax from the system. But also, you want devices where, depending on whatever control parameter you have, if you change that control parameter, the energy, the frequency of your qubit or the energy of your qubit doesn't change. And the goal is to try and find a way to get both of these in the same qubit. And it's actually really hard to do. So every qubit that we have is either really good at one or really good at these other things. And so last year, my group, I'm going to skip ahead all the reason of why, blah, 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 designed this new sort of more complicated qubit that has 2 junctions, 2 capacitors, and 2 arrays of junctions. And by doing this, you can actually realize one of these double well potentials that's still insensitive to noise. And so this allows us to build something that now is no better than the Transmon in terms of the material properties, but instead of a few hundred microseconds T1, information will live for 1.5 milliseconds. And it's still fairly insensitive to T2 to noise. And so this is the kind of thing you can do building a qubit that is insensitive to noise. And I'm going to skip ahead with all the details. The last thing you might want to do is quantum error correction, right? And that's sort of the big thing that everybody's seeking right now. One of the big goals of our National Quantum Initiative Center, the Co-Design Center for Quantum Advantage, this big DOE center that we're running with all of these places that are part of it, including Harvard. Mir Jacobi is part of our center. We're sort of building the bridge to the post-NIST. That is, we're trying to build to the point where we can use this sort of active quantum error correction. But right now that doesn't happen, right? Nobody's really successfully done this to correct all errors. And so when that happens, we just say we're in the NIST era. NIST stands for Noisy Intermediate Scale Quantum Computing. And that's what you read about, Google's quantum supremacy experiment was taking 50 qubits with no error correction and doing something that's very hard. In our group, we do this in sort of different ways. So we sort of say, rather than doing pure, digital quantum computation, we're going to take the pieces of quantum computers and we're going to try and do like cool physics experiments with them by building them into weird systems. And the idea here is like, the opposite of quantum computing. So in quantum computing, what you do is you take two qubits and then you mediate an interaction between the qubits based on photons. And we basically do the opposite in our NISCAF. So we take one qubit and we use it to mediate interactions between two photons. And that allows us to look at many body physics experiments with light. And so we've been able to build, by building arrays of cavities and with qubits, you can basically, look at what happens when you allow photons to interact. And we've seen, phase transitions of light in different ways. And we've built new scanned probes like a quantum gas microscope that allow us to look where the photons are. We've built things where we look at bound states of photons and scattering off of bound states. We've looked at, non-Euclidean lattices, because in superconducting systems, you can sort of basically lithographically draw what lattice you want. And so we can build projections of non-Euclidean planes onto a flat plane and build devices that let us look at like interacting photons, in curved space. We can look and build new kinds of flat bands, and in band structure physics, flat bands are super interesting because any arbitrary amount of interaction is a dominant energy scale in the problem, and it gives rise to all kinds of new physics. We can look at what's called ultra strong interaction, where the rate at which an atom wants to absorb a photon is bigger than or comparable to the frequency of that photon, and what does that mean, and what kind of physics happens. And we can look at like topological structures that emerge. And all of this stuff is sort of a spectrum from, relatively simple experiments to very complex experiments, and things that are sort of really very much drawing on non-equilibrium condensed matter physics, and interesting many body results to like, the deep mathematics of these hyperbolic lattices and these flat bands, and how you can build lattices with flat bands. And so this is sort of the last flavor of thing we do in the group, which is, essentially use the fact that all of our circuits are lithographically defined. And so we can draw whatever we want to do sort of weird new kinds of physics that you can't do with real materials by simulating them with these circuits. If I had more time, I would go on and tell you details of a couple of these things, but it's a little bit out of time. We're already a little bit over, and I want to leave time for any researchy questions. But this is sort of a fun interplay between now the devices, the math, and the physics all together to try and see the kinds of experiments we can do. And so really that's I think a good stopping point, which is just to say, the three flavors of research my group does right now, which I think are like three super fun branches of quantum science, are one, really like understanding the microscopic origins of loss and why there are errors at all in quantum computers. Two, trying to invent like new kinds of qubits or couplers that exist in the real world but don't care about the sources of noise that we can't get rid of. And then three, taking the pieces and building them into sort of fundamentally interesting systems that lets us do cool new quantum science that's really, maybe not quite quantum computing, but it lets us like use the pieces that we built for quantum computing to just do and study cool physics. And I think those are the three real flavors of things we do, and hopefully that gives you some idea of what we care about on the research scale. So I'm happy to take questions about any of that. I know it was super fast on the research. I'm sorry I went very long on the personal personal biography.
Are there any questions? Please feel free to raise your hand and unmute. If not, maybe I'll ask something super briefly. But this ultra strong interactions, you said like there's this G and this omega C. What's the kind of like rate that you can, what's the ratio?
Yeah, so G is like the rate at which a qubit will absorb a photon from the cavity, and omega is the photon frequency. And in this experiment that I sort of am showing on this picture here, we actually are looking at how the dynamics of the system change as we tune G. So we can actually tune G as an in situ parameter, and we can bring it up to something like 0.7 omega. So, about 70% of the frequency. So our frequencies are something on the order of 5 or 6 gigahertz, and we can bring G up to like 4 gigahertz.
Dissipation is like super small, or like
oh yeah, and dissipation in all these systems is something like I guess in some of our better systems, it's sub-kilohertz, but it's on the order, even in our worst systems, it's a couple of kilohertz. So, it's G's are gigahertz and dissipations are kilohertz.
I see a question in the audience from Keshav. You can go ahead and unmute and ask your question.
Professor, I wanted to understand something because you mentioned bound photon states. And while I have seen a very limited amount of work on, say, bound photon pairs regarding elementary particles, I do not know if it's possible to do this with, say, many photons. If you could comment on that, and if that is possible or linked to your research.
Yeah, so the bound photon states are sort of what you get when you have essentially a defect in a photonic crystal or a defect in a crystal. It essentially opens up, essentially a bound defect. But there tend to be, single photon states. What we're looking at in these ultra strong interacting systems is the onset of multi-photon bound states. And what we can see is that you can get, up to not just two, but even, we can see the effects of a 3-photon bound state there. And so that's really what happens as you really turn the scattering rate way up with this G. That's actually what we're investigating in this ultra strong paper, which is not out, but will be soon, hopefully.
If I may follow up on that, I remember seeing some work like this in coupled systems in nonlinear dynamics, primarily on graphs in the classical format. And how similar is the math for, say, many photon bound states to, say, coupled dynamical systems in classical nonlinear dynamics?
Yeah, so there's a continuum here, right? So if your interactions are relatively weak, and in some of our experiments we use relatively weak interactions, then it's basically a nonlinear wave equation type system. As the effective interaction strength gets strong, though, then every time you add a photon to the cavity, it shifts by more than a line width, and the quantized nature of the electromagnetic field becomes important. And so it's really, whether it really is sort of classical nonlinear optics and nonlinear dynamics or quantum physics really depends on whether the nonlinearity has a significant impact at the single photon level or beyond. And we can certainly get to the point where it's single photon and therefore quantum.
I see, because when you mentioned a continuum, I was thinking that it's somewhat of a departure compared to what I'm used to thinking, because whenever I've seen dynamical systems, with most systems, you tend to come up with, say, bifurcation models pretty well.
Yeah.
So if there's a continuum, so would there not be a bifurcatory behavior, or does the continuum still hold?
Yeah. So if you drive the system hard enough, it'll almost always bifurcate. And if you have a weak nonlinearity, then that's kind of what you like, the only physics that you tend to see. If you have a strong nonlinearity, then you can sort of see some interesting things before bifurcation sets in. So you see things like photon blockade, where only photon can be in a resonator at a time, and it gives you like anti-correlated photons coming through and other things like that. And so in this multi-photon bound state thing, you see sort of an entanglement that's spontaneously being generated by scattering off of this bound state. And so there's things that are sort of interesting and quantum mechanical that's on before you see the bifurcation physics. But certainly if you drive the system hard enough, it will bifurcate.
So bifurcate into what actually?
It'll become like a multimodal system. So you'll tend to see the nonlinear amplifier will the stable state will essentially bifurcate. So the peak basically tends to bend over, and then when it sort of bends completely over, you get sort of a bifurcation in the amplitude stability.
Thomas and then Harry, and then we might try to wrap it up.
Hi. I was wondering, where do you think Transmon superconducting qubits need to go before they can kind of expand the computers into like the 1,000 qubit range?
I mean, I feel like every physical system can kind of get to 1,000 qubits. I think going beyond 1,000 is going to be quite hard, but most of the, it's really, you can sort of brute force get to 1,000 qubits with transmons. I think you'd like to see them be a little bit better. I think as you build bigger systems, you have to worry about correlated errors and crosstalk and things like that. But but I think the real challenges get to be, if you need millions of qubits because you have these sort of inefficient approaches to error correction, then then really building very large scale systems becomes quite a difficult challenge. But 1,000 is not, we're going to see 1,000 in a few years, I would bet.
Okay, thank you.
Very good.
Thank you for the great talk on both the personal journey side and the scientific side. I have a question more related to this last part where you're talking about doing many body physics in these types of superconducting circuits. From my previous understanding, a lot of times like things like disorder and things like the number of control lines, there are a lot of engineering challenges for trying to really get these things done really well in an academic lab. So I was wondering if you could comment a little bit on kind of those challenges, as well as how to find angles to maybe either overcome them or find problems that maybe others who have more capabilities, maybe in industry, aren't necessarily looking at, but can still be done in an academic setting.
Yeah, there's a few different things that you can do there. It's a really good question, right? So on one hand, one thing you can do, and we did this in some of the bigger systems with our earlier work, is you essentially accept disorder and you look at the influence of disorder, or you can trade off between universality, right? So you're not building a universal quantum computer, but you can then build one that's bigger because you're not enforcing universality. There are ways that you can if you want to control everything, you can put in a little magnetic line and tune every qubit up to be perfect, and that's something that you can do even at the sort of dozen qubit level in an academic lab without too much problem. You can go beyond that, right? So there's some new RF system on chip type cards that might bring the cost per channel of the electronics way down, so that you could imagine doing that for even more qubits, and that's something that's like I've been super excited about. There are techniques you can use to, at room temperature, tune up the fabrication. So IBM has an approach where they zap things with lasers, but there's other things you can do to tune up the qubits before you cool them down, so you don't need as many wires. It's true that at some point you'll be able to do anything you want in terms of digital quantum computing with giant quantum computers. But if they're always built in a certain architecture, and I think you can get incredible efficiencies at simulating and asking interesting questions by laying out your qubits in non-standard lattices. So rather than having just your regular 2D square grid of qubits, you can build some of these crazy lattices we show here, which intrinsically encode really interesting physical properties. And so you can get significant advantages over commercial processors by cleverness in what you lay out. And the thing that you get in an academic clean room that you don't get in an industry clean room is real speed, right? So these industrial processes are quite good and can build really very complex things that we can never build in an academic clean room with like incredible coherences across the chip. But there's a whole pipeline, and they can't experiment with what materials are allowed, and they can't just be like, I have this new idea, let's just like throw one of those in and make that, right? Whereas my student can lay out a new device and fab it in a couple days and get a new thing in the fridge. And so there's a speed and flexibility that you have in academia that you don't have in an industrial setting. And so I think that the pairing of those allows us to really explore a sort of much broader and more interesting space than either one could on its own. And so I really actually enjoy working with my industrial collaborators. And I feel like it's, in some sense, the onset of real industry and quantum computing has really helped my research because, I'm less interested in building large universal scaled systems. And I think it allows me to think about what are the interesting things I can do either with particular application specific problems or with particular components without having to then go and build like a 50 qubit universal quantum computer like Google did and like try and run the thing, because that's not something that I would be particularly good at. And so I feel like academic groups and industry groups can complement each other quite nicely and push the field further in ways that neither could do on its own.
Yeah, thanks a lot. I guess since you mentioned towards the end about the current status of industry and academic collaborations, could you say a few more, maybe short sentences about that as well?
Yeah, I mean, I'd say right now, industry and academia are collaborating quite nicely. There's always some challenge in this because industry is going to care about IP and they can't tell you everything they do. But I've had long collaborations with folks at IBM. I know I've at least talked to people involved at other companies. Maybe to a lesser extent than I have with IBM. But I think it's really right now a very healthy and vibrant ecosystem. Who knows where things will be in a number of years, right? Like it's also like industry needs extremely well-trained people, and we're producing them. I think when I started my faculty job in 2008, there was almost no industry efforts in quantum computing, which is, it's not that long ago. And I was worried, what would my students do when they graduated? Because some of them might get faculty jobs, but if they don't do that, like what skills will they learn that can translate to some other thing? And by the time my first student graduated, industry was already really doing this. And now, some fraction of my people go on to academia, but almost everyone in my group is still doing some kind of quantum science, either at a company or in an academic group. And so there's just so many opportunities for people that it's really exciting to me that like there's like a rich research ecosystem and a lot of opportunity for my people to like do the things that I help them learn how to do, and that's just super rewarding.
Thanks a lot.
So I kind of wanted to ask a question, and I feel free to not answer this, or also we can shut off the recording or whatever you'd like. What's your social security number? No. But the question I wanted to ask was something like, so last week there is this thing that was widely circulated about from Professor Galitsky at Maryland about quantum computing, and it seemed both super provocative and also like, I don't know, super provocative, but like provocative and like unvarnished a little bit in terms of like kind of contrary to some of the optimism there's been about, or hyper optimism there's been about quantum computing recently. Do you have any, at the risk of sounding too Gen Z, do you have any thoughts or takes on this? Or
I mean, yeah, I mean, I would say, there's a spectrum on everything, right? I think, there's certainly people who will tell you exactly what you want to hear about how quantum computing is going to change everything. I think there's people who are much too pessimistic that it will never work. I think, I don't see any reason why quantum computing, I think it's a guarantee that we're going to get to like 1,000 qubit quantum computers in not that long. I think there are some real roadblocks to getting well beyond that, but they don't seem insurmountable. I think the overall impact of quantum on the world is something that I think we don't fully understand yet, right? We know it's like the first, or it's almost assuredly the first different kind of computer that we've ever built, right? It's almost certainly something that's beyond like the sort of Turing machine, but we don't know exactly what it will be sort of most powerful for. I think within that, right, like then there's questions of what you're comfortable with. I think industry groups have different incentives than academic groups, right? They're not out to publish papers and do good science, they're out to build tools. Some of that involves raising money, and people have to raise money by selling things, and so it's a different process. I think when a huge fraction of academia is also tied up with industry, it does tend to blur lines a little bit when people have to be true to what we as scientists want, which is a pursuit of truth, and their other hat on, do what they need to do for their companies. I would rather everybody not oversell things and work together, but I think you need companies in order to get things done like that. And so it does feel overheated to me right now, like the overall business investment seems a little bit overheated and overhyped.
in the short run, but in the long run, I think I'm still a real quantum computing optimist. And I expect that we will build them, and I suspect that there will be many applications that are really quite important, if not sort of rewriting all of how we think about computing.
So just to clarify, on the scale of Scott Aronson to Chris Monroe, you're about a 6.
Yeah, I mean, I'm the question, yeah, exactly. I'm somewhere in the middle, I would say, right? That, and I think it really is, short term, long term, or like there's so many definitions of impact. So I'm somewhere sort of, I think I'm still very optimistic, but not that the world will be changed in 3 years.
Awesome. With that, Andrew, you wanna give us some parting words?
Thank you.
It's a lot of words. I was getting nervous there.
Yeah, so wonderful. So I wanted to thank you again, Professor Houck, for an excellent conversation today. And thank you also for staying so long over time. Very much appreciate it. And thank you all in attendance for your interest in Chilloquium as well. We have a really exciting lineup of speakers for the rest of the summer, with talks in future weeks from a number of physicists involved in quantum information science, including Professor Tachi Mamoglu from ETH Zurich, Emmanuel Bloch of Max Planck, Michel Devoret of Yale, Jun Ye from CU Boulder, Monica Schreier-Smith from Stanford, and many more. Thank you all very much, and see you next week for a talk with Tachi Mamoglu of ETH Zurich. Thank you again, Professor.
Thanks, everybody.